Good evening, students. I'll start with the class. In the previous class, I started with a new chapter, that is mechanical properties of fluid. We had seen something called as pressure. Pressure is nothing but force exerted upon a certain area. Okay, there's an area and there's something. The area in contact with the surface. This will be the area. How much of force has been applied on that particular area is nothing but the pressure. We had seen pressure is force upon area. This will be one formula which will be used to solve the problem. Sometimes if needed, force can be also used as mg, mass into gravity, where F is equals to mass into gravity. Then we are seeing what is Pascal's law. Pascal's law states that anything is there in the liquid, okay, then all the pressures are always equal. Pa equals to Pb equals to Pc. We had derived one equation also. All the pressures acting on a non-compressible liquid, something is always equals to always the same. Even then we had seen for a hydraulic machine, we use a smaller tube here and a bigger tube. There are always two pistons, both the sides. Okay, this side it will be F1, pressure 1, area 1. This will be the area of the first piston. Same way, this pressure P1 is transmitted till here and will go over here as P2. So P2, then this will be the force exerted on this piston will be F2, and consider the area as A2. Then pressure as per Pascal law is always equal. F1 upon A1 will always be equal to F2 upon A2. This is another one needed to solve the problem. These three things you should know. We're supposed to solve the problems at the end of the chapter, but I will solve it now itself because this is a separate topic, problems. Then later surface tension problems will be different. So based on this concept, I solve problems now. There is simple ones. Questions are already there on the notebook and not on the notes. These notes are given to you all. Those who have not attended the previous class, that recording and have not gone through, just look out for these notes. I had given you all the notes. That is mechanical properties of fluid. Just check in those. You will have it. Now I'm on page number 3. So there are problems. Page number 3. Those problems I will solve. Question number 1. The two thigh bones, each of a cross-sectional area 10 centimeters square, support the upper part of a body of mass 40 kg. Estimate the average pressure sustained by the bone. Okay, so the legs of the bones of the leg, which is having the area of cross-sectional area of 10 centimeters square, support the upper body. which is of mass 40 kg. We have to calculate the pressure. So mass given, how much mass it has to support is given as 40 kg. Cross sectional area means the area which is in contact with area. So both the legs. So one leg is thigh bone is 10 centimeter square. So that will be total will be how much? Total area for both the legs. So 20 centimeter square. Because both the thighs bone is supporting 40 kg. Centimeter square means 10 raised to minus 2 square, which is 20 into 10 raised to minus 4. Convert it in standard form. It will be in terms of meter square. This is 10 raised to meter square. Total area. G we have to take as 10. We have to calculate pressure. So pressure is force upon area, but now force has not been given. I have told you instead of force, you can also use the formula pressure is upon area. Mass is given as 40 kg, gravity is 10, and total area is how much? 20 into 10 raised to minus 4. Now calculate and write the answer. One will be less, or take this up, 10 raised to 1, not less, sorry. This is minus, no? So it will go up. 2 into 10 raised to 5 pascals. Unit of pressure is pascals. Next question. A 50 kg girl wearing high heel balances on a single heel. Okay, just one heel. The heel is circular with a diameter of 1 centimeter. What is the pressure exerted by the heel on the horizontal floor? So the heel, okay, is of 1 centimeter diameter, which is across the. Now this is the heel which is touching the floor. So the area in contact with that only. Radius is given, diameter is given, sorry. Diameter of the heel is 1 centimeter. Only one heel, okay? If there were two heels, then you have to area double, like how for the previous one, two bones we had considered double, no? But now they have specifically mentioned just one heel. The mass is 50 kg, diameter is 1 centimeter, so radius will be 0.5 centimeter, which is 0.5 into 10 raised to minus 2 meters. Always the conversion to convert into meters. If it was area, then it would have been square. So what will be the area area will be pi r square because it is circular hill. So 3.14 into 0.5 into 10 raised to minus 2 the whole square. This will be 3.14 into 0.25 into 10 raised to minus 4 is the area. Now pressure has been asked to calculate. Mg. You can use 10 only if you want, or else 9.8. If not specified, you can use it as 9.8 also. Mass is 50. Area is this 3.14, 0.25 into 10 raised to minus 4. That will be pascals. You just frame the questions and give your calculation part, then you will do. Next one. Third one. How much pressure will a man of weight 80 kgf exert on the ground? First is when he is lying on the floor, and the second one is when he is standing on his feet. Now, when given that the area of the body of the man is 0.6 meters square, and that of the foot of the leg is 80 centimeters square. I'll frame the question and give. Third one. Now mass just here. Now mass is not given. Weight is given. Weight is given as 80 kgf. Means what? You have to multiply it with, straight away it's like mg is directly given to you. Weight means mg, which is 9.8. Whenever something like this kgf is given, automatically you have to multiply it with 9.8. Then what else is given? First case, when he's lying. So what will happen when he's lying? The whole area will come in contact. So this will be the area in contact. So how much has it been given? Area is given as 0.6 meters square. So no need to convert, it is in terms of meters only. So pressure will be straight away, that is directly mg upon A. So total mg is this. Eighty into 9.8 upon 0.6. And second one, standing. So what is going to happen when standing? Only the foot will come in contact with the surface, and that area is given as, so your foot will come, the whole body will come in contact with the surface. foot area is given as 80 centimeter square. So we'll have to convert it. 80 into 10 raised to minus 4 meter square. 1 centimeter is 10 raised to minus 2 meters. And then there's a square. Only area will change now. This will remain the same. A foot, no, 1 foot. Sorry, wait. Standing, no. Both will be considered, no. Both the legs. Here they have not mentioned is standing only on one leg. So both feet will have to consider. So total, this is a one leg or 1 foot. So both feet will be singular of this is foot. When you use both the legs, it is called feet. So 2 into 80 into 10 raised to minus 4. So use 2 here. If 9.8 may not give the correct this, you can use 9.8 or 10 also. This will be 9.8, so it will be 4.9. Then this will go up. Newton per meter square you can use, or you can mention pascals. Both the ways it is correct. Whether you can write pressure in terms of Newton per meter square or Pascal. If anyone having doubt in this, you can ask her. And the fourth one, they say find the pressure exerted against a board of the force now. Force is given 20 Newton. Area is given as 0.1 mm square. This is straight away. The pin, you're keeping a nail, applying 20 Newton force, area is this. So pressure is straight away force upon area. So 20 upon mm it is, oh okay wait, this is mm not meter. So this will be 0.1 into 10 raised to minus 3 now. Then whole square. Because 1 mm is 10 raised to minus 3 meter. This will be minus meter square. This is Newton, and this is meter. Twenty into 10 raised to 7 Newton per meter square, or can use Pascal. You can also write this as 2 into 10 raised to 8. 0 if you multiply it will become 10 raised to 8. Both the ways correct. So if mass is given, you have to use mg here. If force is given, straight away force upon area. Next question. Based on the hydraulic lift or the Pascal's law, hydraulic automobile lift is designed to lift cars with a maximum mass of 3000 kg. The area of cross section of the piston carrying the load is 425 centimeters square. What maximum pressure would the smaller piston have to bear? Okay. There's a hydraulic lift. Will be two. Now, hydraulic lift, the load is always kept on piston 2. The load over here, load means mass of 3000 kg. Area of cross section of this part is A2 is been given 425 mm per centimeter square. M M2 is given. Mass 1 is not, nothing is there. So this side I'll use the letter M2. A2 is also given. And this side pressure has been asked to be calculated. As per Pascal's law, okay, first we'll convert, we'll write this here. M2 is 3000 kg. A2 is 425 centimeter square. So it will be into 10 raised to minus 2 the whole square. Okay. What has been asked? Pressure on piston 1 has been asked. What is the pressure on piston 1? Because the smaller piston, I told you always smaller one piston is always this side. This side is always the bigger side. So means pressure on piston 1 we have to calculate. As per Pascal's law, we know that P1 equals to P2. So here we have to calculate P1. So same we can calculate what is P2. P2 formula, pressure will be what now? Force upon area. The letter 2 will use because we are calculating this side. Now force has not been given, mass has been given, so I can modify the formula as force can be written as mg. G, gravity will remain the same. Just substitute now. Mass 2 is 3000. Gravity you can use 9.8 upon 425 into 10 raised to minus 4. So that would be your answer. After calculating whatever answer you get will be your pressure on the, so this much pressure you have to apply so that it can lift 3000 kg. So this pressure I told you always goes here and exerts force. This always you have to remember P1 equals to P2. Next one, second one, fifth, that was the sixth one. In a car lift, What is it? No, can lift it. I don't know. Not printed properly. Okay, whatever it is. Compressed air exerts a force F1 can, I think. So F1 on a small piston having radius 5 centimeter. This pressure is transmitted onto the second piston of radius 15 centimeter. If mass of the car, okay, whatever can car to be lifted is 1350 kg, what is F1? What is the pressure needed to accomplish this task? Now they have mentioned specifically take gravity as 9.8, 9.81, whatever. 8 only it is, that's the bracket. Okay, same diagram. Now, if you notice, they said the radius. Radius means now the piston is circular. This is a bigger one, okay? Now the pistons are circular in nature because whenever it includes radius, it's understood circular. So what has been given? R1 is given as, this is F1. R1 is given as 5 centimeter. R2 is given as 15 centimeter. Convert it into meters. So this is R1, this is R2. If the mass load is always here, lifting part is always on the second side. So load M2 is given as 1350 kg. What is F1? Same logic. P1 is equals to P2. So this will be F1 upon A1 is equals to F2 upon A2. I want to calculate F1 now. So keep F1 here, take A1 on the other side. Now force 2 has not been given but mass has been given. So F2 I can use it as mg. A1 means area of the first piston. So pi r1 square, area of a circle. And A2 will be pi r2 square. That would be area of the second piston. Pi and pi will cancel. Now substitute the values. M2 is this. Gravity is 9.8. R1 square. 5 into 10 raised to minus 2 the whole square. 15 into 10 raised to minus 2 the whole square. So when you open up the bracket, this will be 1350, 9.8. Pi square will be 25. 10 raised to minus 4. 15 square. 625. Sorry, I told you of 25 square. That would be 165. Right now. Hmm. And then this also will get cancelled. You can calculate the answer. 225. No one is correcting also. Then right answer. You can also do it that way if you don't want to first calculate and write the answer. No, write it 2 times also. See, 1350 9.8. Pi square I can write it as 5 into 5 into 10 raised to minus 4. By 15 I can write 2 times and then 10 raised to. This is again more simpler. So then you can cancel with this. 5 3s are 15. 5 3s are 15. In case you don't want to waste time in calculating the squares. Next question. Also find the pressure has been asked. So calculate pressure to. Also pressure also has been asked. F2 upon A2, which is M2. Area would be pi r square. So 3.14 into r would be 15 into 10 raised to minus 2 the whole square. So this is pressure. P1 is equals to P2. So P2 is what? Force upon area, but force is not given. Mg is given. And area is nothing but area of the second piston. So it's circular, so pi r square. If force is asked, then this also you have to convert in terms of force like the previous part and then take the remaining step like this. Seventh one, area of the smaller piston is 1 centimeter square. Area of the larger piston is 22 centimeter square. How much weight is raised? Weight has been given. I told you kgf has been given. 200 into 9.8. Oh, this is already exerted on the first one. Huh? Just check the question. This is not of the second. This kgf is exerted on first piston has been given. Weight. Now weight on this is smaller one given. So weight on larger has been calculated. Asked to find. So this is what M1G and what is M2G has been asked to calculate. So same thing, P1 is equals to P2. So this will be force upon area. So M1G is equals to M2G. Now this is asked to calculate how much of weight can be lifted. Lifted means on the right hand side, how much load can be lifted when you are giving a force of this much, 200 into 9.8. A1 is this. Don't substitute this sum. You can write answer in terms of kgf only there. So this will be A2 is given as 22 into 10 raised to minus 4. So take this up. kgf will be M2G. That will be answer after calculating M2G, the load on the second piston. M2G is nothing but load on larger piston. And M1G is the load on the load means you are exerting here. This M1G. And then it goes and this side it goes up. Load whichever you have to pick it up. How much it is, whatever is this value. Remaining two of them you just give a try. Okay, I don't know, then you can ask. 8 and 9, I'll try that problem. I'll start with a new topic, that is surface tension. Before starting with the surface tension, I'll just tell you under this topic only, you'll come across something called as a cohesive force and cohesive force and adhesive force. It's a one diagram. What, so we'll see what is cohesion and adhesion difference. Now, if there is any material, whether it may be any substance also, whether it could be some solid or it could be some liquid, anything. We are talking about fluids right now, the chapter. So we will be referring it with reference to the fluids only. Now, cohesive forces will be the forces developed between the molecules of the same material. And adhesion will be with a different material. You look at this, the blue line, the bonds, if you see, cohesion bonds, they are between their own molecules, all the blue color bonds. You see those red color, there's a strip, gray color strip like, that's a different material now. Now these molecules are trying to bond it to that gray color. So that is called as adhesion or the adhesive forces. Within itself, if they are trying to bond, then they are called as cohesive forces. Uh, E will not be there like this, right? This adhesive, cohesive and adhesive. So right and kid, this is forces between own molecules. Force between different molecules, different materials. Same material. So cohesive, what they do, help the substance to remain bounded. Substance will remain bounded. Consider this pen itself. Why is it having this color shape? All the molecules inside this, okay, every single molecule are trying to hold on to each other. Otherwise, what is going to happen if the molecules don't have the force of attraction between them? This pen would be like broken into small particles. It would not exist. Okay, it would be just broken down into small particles, but it holds its shape because of the cohesive forces. Okay, it remains, helps the substance to remain bonded. The adhesive forces means helps the substance to stick or to hold onto another one. It's like adhesive means using like a fevicol glue. Okay, this, there are no adhesive forces here because if I keep the pen here, it would fall. It will not stick. But if I put a chewing gum here, it might stick because the adhesive forces. Okay, so not necessary every material will have to have both the forces. Some might have this as zero, some might have both, some might have only adhesive, but cohesive have to be there because every this would not exist on the otherwise. All the particles would spread out. But adhesive, not necessary all the materials have. Like chewing gum would have, so if I stick it, it would stick it to the wall or to another substance. So the property of trying to stick it to some other material is called adhesion. And then this is helps molecules to stick among themselves. They try to stick among, it's like one family. They are trying to bound within each other. They don't want to mix up with the other family. So based on this, what is surface tension is? If you have a glass and if you have some liquid, okay, there are some water molecules present here, and then this is a surface. This is a surface. There's a different material here. This is a different, because inside there is all water, suppose all fluid, and this side there is air. So these are two different substances now. So what happens is the property where now these molecules, no, they will try to attain minimum area. They try to stick to each other. Now if you're pouring this, what is going to happen is it will not try to spread out. This water tries to come close to each other. Okay, so in this form, it might form this kind of shape, or it could form this thing. We'll see in detail about this. But all the molecules try to attain minimum area. So that's why they try to come close to each other. So that's why it forms like a bubble. So all water, if you try to put, it might not fall out because for a certain limit, the molecules will try to hold each other. It might not start flowing first only. But if you keep on pouring, then what is going to happen is it will go beyond a certain limit. It has limited cohesive forces. After a certain limit, obviously, it cannot hold on to each other, and then they break and fall apart, means they will start flowing out. So in short, surface tension intermolecular forces or molecular forces that try to bring molecules close to each other to obtain minimum surface area. Like a magnet, they try to hold on to each other. They want to shrink it to as much as small space as possible. So that this force, definition wise, is the force per unit length. So what they are trying to say is there is a one imaginary line which is drawn on the liquid. Now there will be some forces acting across this line. Okay, some perpendicular forces maybe. So it is that force per unit length on an imaginary line drawn on the liquid surface acting perpendicular to it on either side at every point and tangential to the liquid surface. It could be tangential also, it could be anywhere. Tangential means at an angle also. So there is some force per unit area which tries to act on the line, imaginary line drawn on the surface of the liquid. So these forces which help the molecules to be bound together. Which one diagram is there in the notes. So with reference to that, I'll explain. They've considered one liquid. Okay, a surface tension is nothing but force acting per unit length. The symbol is similar to that of density, that is rho. That I'll give again. Unit is Newton per meter of surface tension. Now consider this vessel which has some liquid in it. Now they have considered different molecules here. Let A be the molecule which is deep inside the water. So what is happening? That molecule is not in contact with anything else. It is within its own liquid only, surrounded by the same molecules. So which force will be this? What is going to happen? Molecule A is attracted equally in all the directions by the other molecules. Okay, so as a result, overall it is going to cancel out each other. So exactly equal and opposite will be acting on the other one also, side by side molecule. How it will look like. I could see the screen, I was not sure. Wait. Yes, imagine molecule A is surrounded by infinite number of molecules from all the sides. Now, although they have not shown in the diagram, because all the sides. Same way how these arrows are going out, no? From someone else, the arrows will be coming in. So every arrow is going to cancel out each other. So as a result, overall, there will be no net force acting on each other inside the liquid. Now, if you see, even molecule B is completely inside the water only, it's not touching out the surface. Same thing will happen for molecule B also. But molecule C, what is happening is it is half out and half inside. So molecule C is attracted in the upward direction. But what happens? Less number of molecules are up because it's 3/4 inside the water. So the downward force is more. So overall, which is this, it is not going to cancel out each other. All the forces will not cancel. For C, there will be some force acting downward. And for D, what is going to happen? Like very less area is there on top. So maximum force will be applied on molecule D. Less forces are cancelled. A was this. So everywhere how the forces are going out, no? Same way forces will be coming in also. So this will become zero because it's like cancelling out each other. Opposite forces always cancel out each other. B also same thing. Every force will be acted equal and opposite because it's surrounded by all the molecules. But for C, if you see this side, 3/4 is there. So only these forces will cancel out each other. But what about these forces? The outer one which is going out will not be cancelled out. Okay, so there will be overall a downward force which will be acted by this one from the outer area. So there will be some downward force because not all the arrows will get cancelled out. Here, what is going to happen? More the area, more will be the forces. Here might be only 3 arrows might be acting on this. Here, bigger area is outside. Only few areas this will cancel out. So too many will come from the other substance. Could be air molecule also, which is outer than the liquid. So overall, there will be a lot of force from outside which will be coming, and this fellow is not able to cancel out them because only surrounded by few of them outside of its own. So that this will have maximum force acting on it. So force is nothing but the tension. So some tension is created on these molecules from the outer side like this. So no need to write actually, you can just read it on the notes only. It's there. Now examples of surface tensions they have given. The first example is there's a hairbrush. If you see in the picture, a hairbrush means the brush, paint brush. Okay, the hair of that brush, when dipped in the water, spreads out. But as soon as it is taken out, what is going to happen? They will all cling to each other. This is because the brush inside the water, there is water all around its hair. It has no free surface. The tips of the hair remain spread, but when the brush is taken out from the water film, forms contract due to surface tension. When surface tension is created, what is the compulsory thing needed for surface tension? It needs a surface. Reference surface is needed. So inside the water, when you put the brush, is there any surface? No, it's completely inside. So there's no this contact with the air. You can consider this contact with air is like a surface, this imaginary line. So it is truly inside, so there is no surface tension here. Because no surface only, so there will be no tension. So it will spread out as it is. Now the moment you remove out, what is happening? There is some water particles which are there on that. It is wet. Okay, this brush would be wet because all the water particles are deposited on this. The moment you remove out, it every place will get, so it comes in contact. Now this is a surface, suppose it comes in contact with a surface. What is surface tension? I told you the molecules, water molecules will try to stick to each other. They try to shrink. They want a minimum space, so they will shrink and try to come close to each other. That is same as adhesive forces. Water has an adhesive property. They want to stick to each other, all the molecules. Okay, so they, because of the surface tension, they will all try to come close to each other. Surface tension, I told you, is nothing but take minimum area, and that is why the hair of the brush will cling to each other, and in water it will spread out because inside there is no surface tension. It needs a surface for surface tension to act. If you don't understand or not, then ask her. Next one. Next example is a, now before that, the second point, I'll tell you what happens based on the temperature. Surface tension depends on temperature. Higher the temperature, lower surface tension. Okay. Now, when you, this is what? This is cold water. Now you are trying to put oil on this. When you put oil on the cold water, it will spread out. It doesn't come close to each other. They say the oil is trying to spread out on cold water. Why? oil, if you consider compared to cold water, what will be, this will be hot comparatively. When you're putting oil on the cold water, if you see the temperature, obviously this will be hotter than this one. How much hot we don't know. So how much this? So what is going to happen? Higher the temperature, I told you, surface tension of oil is less. Less means what? They will not try to come close to each other. Less tension means less forces. So they will spread. All the molecules will spread. Okay, so this will be the answer. Higher the temperature, lower this. And where this other way around, what is going to happen when it forms bubbles? You know that when this is hot water, this will be cold comparatively. Cold means higher surface tension because lower the temperature, high surface tension. Cold means high surface tension. High surface tension means more force will come more close. So that's why they become like drops. They stick to each other and they don't spread out. So surface tension property is to bring the molecules close to each other. Next topic is nature of the pressure. Suppose based on the this side is the liquid, suppose, and this side is some area. Okay, this is the reference area, and there will be some pressure. This is the reference line. Now both the sides there will be pressure. If it's a flat surface, then there's no difference of pressure. Equal and opposite here. The resultant force will be zero. They will cancel out each other. But if you have like this type, that is called as a concave. There are three ways. Okay, here the liquid can form this type of shape. Whenever you put in the this no capillary tube or a beaker, this might go concave like this. If that is the nature, then the pressure upward is smaller. Okay, this is smaller, this is bigger. Vertically upward force. This is higher, this is lower. And for convex shape, they have just drawn the reference line, okay, with reference to this. If we have a concave one, then this vertical pressure is smaller than the pressure of the liquid. This is V, by mistake I wrote it as P. This here P V is equals to PL. Here PV is greater than PL. The PV is smaller than P. What is this they are talking about is, this is called as the, like, what kind of shape the liquid can take if you put it in some beaker. To give you an example, suppose if you put kerosene, no, because of the surface tension, it will form like this. I'll tell you in detail later on. Okay, it can form like this if you put kerosene. If you put mercury, different liquids can form different shapes. Mercury forms like this. This is concave. The shape it is, whatever shape it is forming, no, there's a word you will come across, also called as meniscus. Meniscus means shape, concave shape, and this is convex shape. Mercury forms like this due to surface tension. This one tries to stick to the surface. All the molecules try to go towards. So just write this and give adhesive. What is going to happen? The molecules of the kerosene wants to stick to the surface of this beaker. They are going towards the beaker. All, so that's why what is happening? There's a depression caused. All these molecules from the center have run away towards the beaker side because kerosene is adhesive in nature. Whereas mercury not friendly with the, what is that, beaker. It does, all the molecules want to run away. So what they have done, whatever is that, they are trying to run away from the surface. So there's a gap created here, and they've all accumulated at the center. That's why this bubble like has happened. They want to run away from the surface. So this is cohesive. Molecules want to be among each other. They want to run away from this. So based on what kind of material property the material or the liquid has, you will get various shapes. If it has no this, just remains as it is, no adhesive, no cohesive, then equal and opposite, and the resultant is 0. So next we'll see there's a derivation. Pressure inside a liquid drop. Whenever you have a liquid drop, okay, just see this liquid drop versus, we'll see what has happens for soap bubble. Liquid drop, if you see, this entire thing is filled up. Full it is, no? The entire drop is filled with water. But if you see a soap bubble, it is hollow inside. Only there will be outer surface of some thickness. Okay, based on that, we will derive. First is for a liquid drop, and then will be for surface. Now, for the soap bubble. Here, how many this are in contact? How many surfaces are created here? Only one surface, because only one layer is in contact with the air here. But over here, how many surfaces are forming? This is like surface 1, this side, inner side, because here also there is air inside. So that whatever border is coming in contact with the air is considered as surface. So obviously there's one surface here and two surfaces. So a soap bubble will have two surfaces, whereas a liquid drop will have only one surface. The first one you are doing for a liquid drop. So consider a liquid drop. We'll assume it to be of radius r, capital R. Now that theory part is there in the notes. I'm not dictating that, just refer that only. As the drop surface is curved, there exists a pressure difference across the surface. This is concave in nature. So obviously there's a pressure. Sorry, concave, no, convex. Third case, no, like this. So the pressure inside is what happening. The drop is more than the outside. So what is going to happen? The pressure is more, so it will try to expand it. So consider now this bubble, or there is a change in the area. Now the inside pressure is more. So what is going to happen? The bubble will try to, this what is that, drop will try to expand. So consider there was a, it has increased its area by how much? Small distance dr. So total will be how much? R plus dr. Originally, suppose the drop was this much, but because of the pressure, it has expanded slightly. So that will be R plus dr. Drop enlarges. New radius will be R plus dr. Then definitely surface area also will increase from S1 to S2, you can consider. So we have to calculate what are the new changes, the difference in the area. So S1 surface area of a circle, you know that it is 4 pi r square. This is surface area of any sphere. So now, since we are using S1, the original radius was S1. What will be S2 then? 4 pi, the new radius, that is r plus dr square. So this is S1 and this is S2. So change in area will be final minus initial. This minus this. We'll take out 4 pi common. Now use the a plus b the whole square formula. We know that a plus b the whole square is a square plus 2ab plus b square. Four pi a square plus 2ab plus b square. This is dr is extremely small, very small. So what we can do? Dr square will be even more smaller than that. So dr square can be neglected. So this almost equals to, like, it would be 0.0000 something after squaring. It's almost taken to be 0 only. This is assumed to be 0. So this will be 4 pi into 2r dr. This is equals to 8. Change in this is to be considered as ds. Mark it as equation 1. Work done is always, now for surface tension it would be surface tension into, it's like force into displacement. Surface tension also is nothing but force. What is the displacement here? Area has got displaced since the change, that is ds. Also we know that work done is nothing but force into displacement. This is surface tension. Huh? This is also W only. Force displacement is done in terms of radius also. How much distance has it moved to? dr. You know that pressure is force upon area. Pressure is nothing but force upon area. So what is force? Pressure into area. Area of this is what? Of the drop? 4 pi r square dr. This you can put 2, this is 3. If you see both are work done, 2 is equals to 3. Equation 2, this is also work done, this is also work done. So equation 2 equals to equation 3. So equate both the this. So rho ds is nothing but p 4 pi r square dr. Put value of ds from equation 1 over here. ds we had got it as 8 pi r dr. Then cancel whatever is getting cancelled. This r if is capital, dr will cancel. Pi and pi will cancel. 4 2s are. So p you keep here only. 1 r is left. Sigma upon r. So this is what you will get after calculation. After cancelling out, 2 sigma upon r will remain. Out of r square, okay, 1 got cancelled. 1 left, so I brought it here. So this is the pressure for a bubble, for a liquid drop. If you have understood it, the second one is only starting only I need to frame. Rest everything you just follow as it is. Same like this one. This part from here to here, no, this will be same for the soap bubble also. From here to it, which is that this part. I'll show you. We'll do it for soap bubble. So we know that bubble is a hollow sphere. So now what is going to happen? So it's going to be like this. Originally, if it is like this, after expanding, means if this surface is also increasing, I told you there are two surfaces. So if the first surface is increasing, then even consider to be, so they are considered of almost equal length because it's very thin, no? Because this layer is so thin. Okay, so total it's like having two surfaces are increasing simultaneously. If S1 and S2 is also increasing, here also S1 and S2 is increasing. So two surfaces to be considered. Rest the same thing which is there in the notes you write. Then you know it's S1. Now everywhere you have to take double, 2 times. Why? Two surfaces are there. This whole thing is to be taken as 2 times. This also taken as 2 times. Because two surfaces are in contact with the air. So everywhere you just have to only double up. So this will be 8 pi r square. S2 will be, or you keep it as 2 only. 2 times 4 pi r square. And S2 also, then S2 minus S1, 2 you keep out, main, common, 4 pi r square minus 4 pi r plus dr square. Then take out 4 pi out, so it is going to be 8 pi r square minus r plus dr the whole square. S2 minus S1, no wait, ulta. This will be plus, this is minus. S2 minus S1. Same exactly like the previous one, only all continue. Only it will be double now. So wherever you got 4, you would get 8. Wherever if you get 8, you would get 16 that way. So finally, the same thing you carry on. So your only different thing would be ds. The rest everything will remain same. So ds you will get as 16 pi r dr. So this will be equation 1. After that, continue same, copy paste as it is like previous one. And then last, after while substituting, this would be 16. Your final answer will be, instead of 2, it will be 4 then. Why this 4 came? Because we are considering 2 times the surface. So this will be for the suburb. This is S2 minus S1. Only thing by mistake I wrote that first. So I just change the sign. Follow exactly like the previous problem, previous derivation, with only these 2 extra. I'll stop here. Next class I'll start with angle of contact.